Good morning, dear students. My name is Farhan Mazhar, and the subject today we are studying is Cambridge O Levels Physics 5054. In this video, we are going to revise the new chapter added into the syllabus of the Physics 5054, that is the space physics. And today in this video, this is based on the literature which is related with the IGCSE. So the topic of the space physics in the IGCSE, this revision video is based on that concept. The literature which I am showing in this video is not created by me. I have taken this literature from the website savemyexam.co.uk. So the first topic which is coming on your screen is the Earth, Moon, and the Sun, the Earth's axis. The Earth is a rocky planet that rotates in a near circular orbit around the Sun. It rotates on its axis, which is a line through the North and the South Pole. The axis is tilted at an angle of approximately 23.4 degrees from the vertical. The Earth completes one full rotation, or you call it revolution, in approximately 24 hours, which is one day. This rotation creates the apparent daily motion of the sun rising and setting. Rotation of the earth on its axis is therefore responsible for the periodic cycle of day and night. Day and night, the earth's rotation around its axis creates day and night. Day is experienced by the half of the earth's surface that is facing the sun. Night is the other half of the earth's surface facing away from the sun. So you can see in this diagram the face of the earth which is facing the sun. Here we will have the day, and this face which is facing away from the sun, here we will have the night. So you can see this is the vertical axis, and this is the axis of the earth which is tilted, and this angle is some 23 point some degrees, 23.4 degrees. So day and night are caused by the earth's rotation. Rising and setting of the sun. The earth's rotation on its axis makes the sun looks like it moves from east to west. At the equinoxes, the sun rises exactly in the east and sets exactly in the west. Equinox, meaning equal night, is when day and night are approximately of equal length. However, the exact location of where the sun rises and sets changes throughout the seasons. In the northern hemisphere, which is above the equator, in summer, the sun rises north of east and sets north of west. In winter, the sun rises south of east and sets south of west. So here we have a diagram. So these are the equinox. This is the sun in the winter. This is the sun in the summer, and this is the noon time. The sun rises in the east and sets in the west. Its approximate area changes throughout the year. The sun is highest above the horizon at noon, which is 12 p.m. In the northern hemisphere, the daylight hours are longest up until roughly the 21st June. This day is known as the summer solstice and is there where the sun is at its highest point in the sky all year. The daylight hours then decreases to their lowest around 21st December. This is known as winter solstice and is where the sun is at its lowest point in the sky all year. So the Earth orbits the sun once in approximately 365 days. This is 1 year. The combination of the orbiting of the Earth around the sun and the Earth's tilt creates the seasons. So here we have a diagram. You can see this is the 20th March and 21st June, 23rd September, 21st December, 20th March. So this is spring, summer, autumn, winter, and Earth tilted on its axis. Seasons in the northern hemisphere caused by the tilt of the Earth. Over part B, C, and D of the orbit, the northern hemisphere is tilted towards the sun. This means daylight hours are more than hours of darkness. This is spring and summer. The southern hemisphere is tilted away from the sun. This means there are shorter days than night. This is autumn and winter. Over parts F, G, and H of the orbit, the northern hemisphere is tilted away from the sun. The situation in both the northern and southern hemispheres are reversed. It is autumn and winter in the northern hemisphere, but at the same time, it is spring and summer in the southern hemisphere. At the C, this is at C, this is the summer solstice, and the northern hemisphere has the longest day, which the southern hemisphere has its shortest day. So you can see this B, C, D, E, F, G, and B. So they are talking about these positions. At G, this is the winter solstice. The northern hemisphere has its shortest day, while the southern hemisphere has its longest day. At A and D, night and day are equal in both hemispheres. These are equinoxes. Moon and Earth. The moon is a satellite around the Earth. It travels around Earth in roughly a circular orbit once a month. It takes 27 to 28 days. The moon revolves around its own axis in a month, so always has the same side facing the Earth. We never see the hemisphere that is always facing away from Earth. Although astronauts have orbited the moon and satellites have photographed it, the moon shines with reflected light from the sun. It does not produce its own light. The phases of the moon. The way the moon's appearance changes across a month as seen from Earth is called its periodic cycle of phases. So the phases of the moon as it orbits around the Earth. So when the moon is here, this is the first, for example, let's start from here. So when the moon is here on the Earth, you will see new moon. It means that when the moon is here, you will see a waxing crescent moon. When the moon is here, you will see half the first quarter moon. When the moon is here, you are seeing the waxing gibbous moon. Here you will see the full moon, waning gibbous moon, last quarter moon, waning crescent moon, and there will be, again, you will get the new moon. In the image above, the inner circle shows that exactly half of the moon is illuminated by the sun at all times. The outer circle shows how the moon looks like from the Earth at its various positions. In the new moon phase, the moon is between Earth and the sun. Therefore, the sunlight is only on the opposite face of the moon to the Earth. This means the moon is unlit as seen from Earth, so it is not visible. At the full moon phase, the Earth is between the moon and the sun. The side of the moon that is facing the Earth is completely lit by the sunlight. This means the moon is fully lit as seen from Earth. In between, a crescent can be seen where the moon is partially illuminated from the sun. This literature which we were using is written by Miss Lindsay. So calculating the orbital speed, when the planets moved around the sun or a moon moves around a planet, they orbit in circular motion. This means that in one orbit, a planet travels a distance equals to the circumference of a circle, which is the shape of the orbit. This is equals to 2 pi r, the circumference of that circle, where r is the radius of a circle. The relationship between speed, distance, and time is that the speed is equals to distance divided by time. The average orbital speed of an object can be defined by the equation v is equals to 2 pi r divided by t, where v is orbital speed in meters per second and r is the average radius of the orbit in meters and t is the orbital period in seconds. This orbital period or time period is defined as the time taken for an object to complete one orbit. The orbital radius r is always taken from the center of the object being orbited to the object orbiting. So orbital radius and orbital speed of a planet moving around a sun. So this is the orbital radius. This is the orbital speed. So a worked example, the Hubble Space Telescope moves in a circular orbit. Its distance above the Earth's surface is 560 kilometers and the radius of the Earth is 6,400 kilometers. It completes one orbit in 96 minutes. Calculate its orbital speed. You see the total distance from the radius of the orbit will be 260 plus 6,400 kilometers. So the radius will be the sum of these two. The time is 96 minutes. We will use this time in seconds. And we want to find out the orbital speed. The orbital speed formula is 2 pi r divided by t. Step one is the list the known quantities. The radius of the Earth, capital R, is 6,400 kilometers, and the distance of the telescope above the Earth's surface is h, which is 560 kilometers. The time period is 96 minutes. Step two, write the relevant equation, which is v equals to 2 pi r divided by t. So calculating the orbital radius r, the orbital radius is the distance from the center of the Earth to the telescope. So that will be the radius of the Earth plus the height of the satellite above the surface. So the small r will be equal to the capital R plus h. So the center of the mass, and this is the radius of the Earth, and this is the height of the satellite from the surface of the Earth. So the total radius of this track will be, this orbit will be capital R plus h. So that will be 6,400 plus 560 kilometers, and that will be 6,960 kilometers. So then I will apply the formula to convert any units. The time period needs to be in seconds. So 1 minute has 60 seconds. So 96 minutes will have 60 multiplied 96, and that will be 5,760 seconds. The radius needs to be in meters. So 1 kilometer is equals to 1,000 meters. So 6,960 kilometers will be equals to 6,960,000 meters. So now I can substitute the values into the orbital speed equation, which is v equals to 2 pi r divided by t, and 2 pi multiply 6,960,000 divided by 5,760, and that will be equals to 7,592.18, which is 7,590 meters per second approximately. So the exam tip is, remember to check that the orbital radius small r given is the distance from the center of the sun if a planet is orbiting a sun, or the planet if a moon is orbiting a planet, and not just from the surface. If the distance is a height above the surface, you must add the radius of the body to get the height above the center of mass of the body. This is because the orbits are caused by the mass, which can be assumed to act at the center rather than at the surface. Do not forget to check your units and convert any if required. This revision material has been written by Miss Lindsay, and I have taken this literature from the Saved My Exam website. The solar system. The solar system consists of the sun, 8 planets, natural and artificial satellites, dwarf planets, asteroids, and comets. The sun and the planets. The sun lies at the center of the solar system. The sun is a star that makes up 99% of the mass of the solar system. There are 8 planets and an unknown number of dwarf planets which orbits the sun. The gravitational field around planets is strong enough to have pulled in all nearby objects with the exception of natural satellites. The gravitational field around a dwarf planet is not strong enough to have pulled in nearby objects. The 8 planets in our solar system is in ascending order of the distance from the sun are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Satellites. There are 2 types of satellites: natural satellites and artificial satellites. Some planets have moons which orbit them. Moons are an example of natural satellites. Artificial satellites are man-made and can orbit any object in space. The International Space Station ISS orbits the Earth and is an example of an artificial satellite. Asteroids and comets. Asteroids and comets also orbit the sun. An asteroid is a small rocky object which orbits the sun. The asteroid belt lies between Mars and Jupiter. Comets are made of dust and ice and orbits the sun in a different orbit to those of planets. The ice melts when the comets approach the sun and forms the comet's tail. So the objects in our solar system, you can see these are the 8 rocky planets, and these are the, sorry, I said 8. These are the 4 rocky planets, and these are the 4 gas planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Here we have a dwarf planet, Pluto, and here is the moon of the Earth, which is orbiting the moon. Here is an artificial satellite, which is also orbiting around the Earth. The artificial satellite might be orbiting other planets or other moons. So here we have natural asteroid belt that is between the Mars and the Jupiter. Exam tip. You need to know the order of the 8 planets in the solar system. The following mnemonic gives the first letter of each of the planets to help you recall them. My very excellent mother just served us noodles. Some people call it my very educated mother just served us nachos. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Remember this mnemonic. My very educated mother or my very excellent mother just served us nachos or noodles. These are 2 mnemonics for the same thing. Accretion model of the solar system. The word accretion means to accumulate, to come together step by step, gradually, to gradually grow. There are 4 rocky and small planets: Mercury, Venus, Earth, and Mars. These are the nearest to the sun. There are 4 gaseous and large planets: Jupiter, Saturn, Uranus, and Neptune. There are the furthest from the sun. So here we have Mercury, Venus, Earth, and Mars. These 4 are rocky. Jupiter, Saturn, Uranus, and Neptune. These 4 are gaseous planets. The 8 planets of our solar system. These are the 8 planets of our solar system. The difference in the types of planets are defined by the accretion model for solar system formation. The sun was thought to have formed when gravitational attraction of pulled together clouds of hydrogen, dust, and gas called nebulae. The solar system then formed around 4.5 billion years ago. The planets were formed from the remnants of the disk cloud of matter left over from the nebula that formed the sun. These interstellar clouds of gas and dust included many elements that were created during the final stage of a star's life cycle as previous supernova. Gravity collapsed the matter from the nebula in on itself, causing it to spin around the sun. The gravitational attraction between all the small particles caused them to join together and grow in an accretion process. A rotating accretion disk is formed when the planets emerged. So here we have a diagram. So nebula initially is like this. Then here we have the cooler regions. These are the hotter regions. And few million years later, so here we have icy bodies, rocky planets, few million years later. This will happen 100 million years later. This will happen after the 100 million years. You will get this. So the accretion model of the creation of the solar system. So let me reduce the diagram. So this is that diagram. As the sun grew in size, it's become hotter. Where the inner planets were forming near the sun, the temperature was too high for molecules such as hydrogen, helium, water, and methane to exist in a solid state. Therefore, the inner planets are made of material with high melting and temperatures, such as metals, for example, iron. Only 1% of the original nebula is composed of heavy elements. So the inner rocky planets could not grow much and stayed as a small size, solid and rocky. The cooler regions were further away from the sun. The temperature was low enough for the light molecules to exist in a solid state. The outer planets therefore could grow to a large size up and include even the lightest element, hydrogen. These planets are large, gaseous, and cold. The exam tips are, when referring to the accretion model for the formation of the solar system, make sure your answer has the following: the model's dependency on gravity, the presence of many elements in interstellar clouds of gas and dust, the rotation of material in the cloud, and the formation of an accretion disk. This literature which we are using, we use for this topic, is written by Ashika. Ashika. Orbiting bodies, light, speed. The planets and moons of the solar system are visible from Earth when they reflect light from the sun. The outer regions of the solar system are around 5 expo 12 meter from the sun, which means even light takes some time to travel these distances. The sun is so far away from Earth that the light we see actually left the sun 8 minutes earlier. The nearest star to us after the sun is so far away that light from it takes 4 years to reach us. The Milky Way galaxy contains billions of stars, huge distances away, with the light taking even longer to be seen from Earth. The speed of light is a constant, 3 expo 8 meter per second. Therefore, using the equation speed is equal to distance divided by time, the time taken to travel a certain distance can be calculated by rearranging to time is equal to distance divided by speed. So work exam, calculate the time taken for the light from the sun to reach Mercury if the radius of the Mercury's orbit is 5.8 expo 9 meter. So step one, state the equation for the time taken for light to travel a certain distance. So the time is equal to distance divided by speed. So we know the speed of the light and we know the distance of the Mercury from the sun. So step two is substitute in the values the distance traveled in the radius of the orbit. The distance will be 5.8 expo 9 meter, which is equal to the radius of that orbit. The speed of the light is 3 × 8 meters per second. So the time will be equals to distance divided by speed, that is 5.8 × 9 divided by 3 × 8. And the answer will be 1.93333. So the step 3 is round of the answer include units. So it will take 19.3 seconds. So 19.3 seconds. So here it seems some little mistake here. So the final answer is 19.3 seconds. I think this decimal is here. It is 19.333. So we can check. Do we have a calculator here? Calculator. So meanwhile, the calculator opens. I will check this and I will let you know. The speed, let me. So we have 5.8 expo 9 divided by 3.0 expo 8. And the answer will be 19.33. So remember, here we have a little mistake. This decimal is not here. The decimal is basically here. So this is just 1. Okay. So this number is 19.33. So when you round it off, it will be 19.3 seconds. Okay, exam tip is the speed of light is very fast. This is why in our everyday life, things like switching on a light seems to be instant. However, this is only because the light travels very fast and the distances are very small. A large astronomical distances, which can be millions or even billions of kilometers, the limit of the speed of light starts to have an effect. For example, it takes light 8 minutes to travel from the sun to the earth. This means we are seeing the sun as it was 8 minutes ago. If the sun was to disappear, we would not notice until 8 minutes later. Although by that time delay would be the least of our worries. The sun is not going to vanish. So remember, it's just an example. So elliptical orbits of the planets, minor planets, and comets are elliptical, and elliptical is just a squashed circle. Planets, minor planets, and comets have elliptical orbits. However, the sun is not at the center of an elliptical orbit. This is only the case when the orbit is approximately circular. You see, this is the ellipse. So this is the focus, and this is also a focus. The sun is normally on one of the focuses. Planets and comets travel in elliptical orbits, but the sun is not at the center of these orbits. Exam tip: you will not be asked to do any calculation with elliptical orbits. If you are asked to calculate the time period, orbital speed, or radius of an orbit, it can be assumed that it is circular. So remember this. Analyzing orbits. Over many years, data about all the planets, moons, and the sun have been collected. This is not just for general interest, but to indicate factors that affect conditions on the surface of the planets, environmental problems that a visit using manned spaceships or robots would encounter. Table or the data for data of planets in our solar system, So here we have the names of the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. So that is the orbital distance. That's 5.9 million kilometer. This is 108.2 million kilometer, 149.6 million kilometer, 227.9 million kilometer, 778.6 million kilometer, 1,433.5 million kilometer, 2,872.5 million kilometer, 4,495.1 million kilometer. Orbital duration, days of years. On Mercury, it is 88 days. On Venus, it is 225 days. And on Earth, it is 665 days. On Mars, it is 687 days. On Jupiter, it is 11.9 years. And on Saturn, it is 29.5 years. On Uranus, it is 75 years. And on Neptune, it is 165 years. The density, which is in kg per meter cube, the Mercury is 5,427 kg per meter cube. On Venus, it is 5,243 kg per meter cube. And on Earth, it is 5,514 kg per meter cube. On Mars, it is 3,933 kg per meter cube. On Jupiter, it is 1,326 kg per meter cube. On Saturn, it is 6,807 kg per meter cube. On Uranus, it is 1,271 kg per meter cube. On Neptune, it is 1,638 kg per meter cube. The surface temperature of the Mercury is 350 degrees centigrade. The surface temperature of the Venus is 460 degrees centigrade. On Earth, it is 20 degrees centigrade. On Mars, it is minus 23 degrees centigrade. On Jupiter, it is minus 120 degrees centigrade. On Saturn, it is minus 180 degrees centigrade. On Uranus, it is minus 210 degrees centigrade. On Neptune, it is minus 220 degrees centigrade. Uniform surface gravitational field strength, which is in Newton per kg, the G value. On Mercury, it is 3.7. On Venus, it is 8.9. On Earth, it is 9.8. On Mars, it is 3.7. On Jupiter, it is 23.1. On Saturn, it is 9.0. On Uranus, it is 8.7. And on Neptune, it is 11.0. So this is you don't have to remember this data. Exam tip: although you don't need to memorize any of this data, you must be able to confidently analyze and interpret it. Look out for trends such as one variable increasing while the other decreasing or also increases. This carefully about why that may be, with what you have already learned about the planets from this topic. For example, what is the planet made of? What is its distance from the sun, and how does this affect it? This literature which we are using to study this topic is written by Miss Lindsay, and I have taken this literature from the website Save My Exam. Save My Exam. Gravitational effects on orbits, gravitational field strength. The strength of gravity on different planets after an object's weight on that planet. Weight is defined as the force acting on an object due to the gravitational attraction. Planets have strong gravitational field, hence they attract nearby masses with a strong gravitational force. Because of weight, objects stays firmly on the ground. Objects will always fall to the ground, and satellites will keep in orbit, are kept in orbit. So here we have the Earth, the falling objects, the man remains on the Earth, and the satellites keep orbiting the Earth. So the objects are attracted towards the center of the Earth due to its gravitational field strength. Both the weight of any body and the value of the gravitational field strength, G, differs between the surface of the Earth and the surface of other bodies in space, including the moon, because of the planet or moon's mass. The greater the mass of the planet, then the greater its gravitational field strength. A higher gravitational field strength means a larger attractive force towards the center of that planet or moon. G, small g, varies with the distance from a planet, but on the surface of the planet, it is roughly the same. The strength of the field around the planets decreases as the distance from the planet increases. However, the value of the G on the surface varies dramatically for different planets and moons. The gravitational field strength G on the Earth is approximately 10 Newton per kg. The gravitational field strength on the surface of the moon is less than that on the Earth. This means it would be easier to lift a mass on the surface of the moon than on the Earth. The gravitational field strength on the surface of the gas giants, for example, Jupiter and Saturn, is more than on the Earth. This means it would be harder to lift a mass on the gas giants than on the Earth. So here we have, let me increase the size. Okay, so here we have the sun. Its G value is 293.0 Newton per kg. The Jupiter, its G value is 24.7 Newton per kg. Then we have Saturn, its G value is 10.5 Newton per kg. Then we have the Uranus, its G value is 9 Newton per kg. On the Earth, the G value exactly is 9.8 Newton per kg. The Mars, its G value is 3.7 Newton per kg. And on the Moon, the G value is 1.7 Newton per kg. So we have the values of the G for the G on different objects in the solar system. On such planets such as Jupiter, and object's mass remains the same at all points in space. However, their weight will be a lot greater, meaning, for example, a human will be unable to fully stand up. So here we have a diagram. So a person's weight on Jupiter would be so large that a human would be unable to fully stand up. So a body on Earth has a much smaller force per unit mass than on Jupiter. Here on Earth, the G value is 9.81 Newton per kg. This means a body will have a much greater weight on the Jupiter than on the Earth. On the Jupiter, the G value is 25 Newton per kg. Exam tip, you do not need to remember the value of the G on different planets for your exam. The value of the G for Earth will be given in the exam questions. Gravitational attraction of the Sun. There are many orbiting objects in our solar system, and they each orbit a different type of planetary body. So the orbiting objects or bodies in our solar system, the bodies or objects, what it orbits. So the planets, they orbit the sun. Moon, they orbit the planets. Comet orbit the sun. Asteroids, they orbit around the sun. Artificial satellites, any object or body in the solar system. A smaller body or object will orbit a larger body. For example, a planet orbiting the sun. In order to orbit a body such as a star or a planet, there has to be a force pulling the object towards that body. Gravity provides this force. Therefore, it is said that the force that keeps a planet in orbit around the sun is the gravitational attraction of the sun. The gravitational force exerted by the larger body on the orbiting object is always attractive. Therefore, the gravitational force always acts towards the center of the larger body. Therefore, the force that keeps an object in orbit around the sun is the gravitational attraction of the sun and is always directed from the orbiting object to the center of the sun. The gravitational force will cause the body to move and maintain in a circular path. So for example, this moon is orbiting around the earth. So the gravitational attraction of the earth, which is toward the center of the earth, keeps that moon orbiting around in a circular path. Gravitational attraction causes the moon to orbit around the sun, around the earth, sorry. Sun's gravitational field and distances. As the distance from the sun increases, the strength of the sun's gravitational field on the planet decreases. Their orbital speed of the planet decreases. To keep an object in a circular path, it must have a centripetal force. For planets orbiting the sun, this force is gravity. Therefore, the strength of the sun's gravitational field in the planets affect how much centripetal force is on the planet. The strength decreases the further away the planet is from the sun, and the weaker the centripetal force. The centripetal force is proportional to the orbital speed. Therefore, the planets further away from the sun have a smaller orbital speed. This also equates to a longer orbital duration. So the planets furthest from the sun take the longest amount of time to orbit the sun. They travel at the slowest speed. The planets closest to the sun take the shortest amount of time to orbit the sun. They travel at the fastest speed. How the speed of a planet is affected by its distance from the sun. This can be seen from the data collected for a planet's orbital distance against their orbital speed. For example, the Neptune travels much slower than the Mercury. So this table of orbital distance, speed, and duration. So the Mercury, whose orbital speed in million kilometer, whose orbital distance is 57.9 million kilometer. Its orbital speed is 47.9 kilometer per second, and the orbital duration days of year or years is 88 days. Venus, whose orbital distance is 108.2 million kilometer, its orbital speed is 35 kilometer per second, and its orbital duration is 225 days. Earth, its orbital distance is 149.6 kilometers, and its orbital speed is 29.8 kilometer per second, and its orbital duration is 365 days. The Mars, its orbital distance is 227.9 kilometer. Its orbital speed is 24.1 kilometer per second, and its orbital duration is 687 days. The Jupiter, its orbital distance is 778.6 million kilometers, and its orbital speed is 13.1 kilometer per second, and the orbital duration is 11.9 years. Saturn, its orbital distance is 1,433.5 million kilometer, and its orbital speed is 9.7 kilometer per second, and its orbital duration is 29.5 years. And Uranus is 2,872.5 million kilometer, its orbital distance, and its orbital speed is 6.8 kilometer per second, and it takes 75 years for orbital duration. And the Neptune, its orbital distance is 4,495.1 million kilometer. Its orbital speed is 5.4 kilometer per second, and its orbital duration is 165 years. 165 years. He says, be careful with your wording in this topic when talking about gravity. It is important to refer to the force of gravity as gravitational attraction, strength of the sun's gravitational field, or the force due to gravity. Avoid terms such as the sun's gravity, or even more vague, the force from the sun. Orbits and conservation of the energy. An object in an elliptical orbit around the sun travels at a different speed depending on its distance from the sun. Although these orbits are not circular, they are still stable. For stable orbit, the radius must change if the comet's orbital speed changes. As the comet approaches the sun, the radius of the orbit decreases. The orbital speed increases due to the sun's strong gravitational pull. As the comet travels further away from the sun, the radius of the orbit increases. The orbital speed decreases due to the due to a weaker gravitational pull from the sun. So if you look at this, this is an elliptical orbit. So when the comet is near the sun and it is fastest, and when it is away from the sun, somewhere here it is slowest here. So the comet will be here fastest, and here it will be slowest. Comets travel in highly elliptical orbits, speeding up as they approach the sun. Conservation of energy, although an object in an elliptical orbit such as a comet continually changes its speed, its energy must still be conserved. Throughout the orbit, the gravitational potential energy and the kinetic energy of the comet changes. As the comet approaches the sun, it loses gravitational potential energy and gains the kinetic energy. This causes the comet to speed up. This increase in speed causes a slingshot effect, and the body will be flung back out into space again, having passed around the sun. As the comet moves away from the sun, it gains gravitational potential energy and loses kinetic energy. This causes it to slow down. Eventually, it falls back towards the sun once more. In this way, a stable orbit is formed. So exam tip here is, remember that an object kinetic energy is defined by 1 by 2 mv square, where m is the mass of the object and v is its speed. Therefore, if the speed of an object increases, so does its kinetic energy. Its gravitational potential energy therefore must decrease for energy to be conserved. The literature we are studying for this revision, and this literature especially, this is written by Miss Katie, and I have taken this literature from the website Save My Exam. The sun as a star, the sun lies at the center of the solar system. The sun is a star which makes up over 99% of the mass of the solar system. The fact that most of the mass of the solar system is concentrated in the sun is the reason the smaller planets orbit the sun. The gravitational pull of the sun on the planets keep them in orbit. The sun is a medium-sized star consisting of mainly hydrogen and helium. It radiates most of its energy in the infrared, visible, and ultraviolet regions of the electromagnetic spectrum. So this is an image of our sun. Stars come in a wide range of sizes and colors, from yellow stars to red dwarfs, from blue giant to red supergiants. These can be classified according to their color. Warm objects emit infrared, and extremely hot objects emit visible light as well. Therefore, the color they emit depends on how hot they are. A star's color is related to its surface temperature. A red star is the coolest at around 3,000 Kelvin. A blue star is the hottest at around 30,000 Kelvin. So here you see this color means 30,000 Kelvin temperature. A star of this color means 20,000 Kelvin. This color means 10,000 Kelvin. This means 7,000 Kelvin. This means 6,000 Kelvin. This color means 4,000 Kelvin, and the red color means 3,000 Kelvin. The color of a star correlates to its temperature. Nuclear fusion, and in the center of a stable star, hydrogen atoms undergo nuclear fusion to form helium. The equation for the reaction is shown here. So here we have the protium and the tritium, and they join each other, they fuse into each other, and they make the nucleus of helium, and one neutron is given out. Deuterium and tritium are both isotopes of hydrogen. They can be formed through other fusion reactions in the stars. A huge amount of energy is released in the reaction. This provides a pressure that prevents the star from collapsing under its gravity. So here we have a diagram. You can see the deuterium and tritium. They fuse into each other. They make helium. They produce energy, and a neutron is given out. This is nuclear fusion. The fusion of deuterium and tritium to form helium with the release of energy. So here we have an example of a hydrogen fusion reaction which takes place in the stars is shown here. So hydrogen 1,2 plus hydrogen 1,1 is equal to helium 2,3. Which of the following is a valid reason as to why hydrogen fusion is not currently possible on Earth? Hydrogen fusion produces dangerous radioactive waste. Hydrogen nuclei required very high temperature to fuse together. Hydrogen is a rare element that would be difficult to get large amount of. Hydrogen fusion does not produce enough energy to be commercially available. Answer is B. Hydrogen nuclei require very high temperature to fuse together. Hydrogen nuclei have positive charge, so two hydrogen nuclei would have a repulsive force between them. High temperatures are required to give the nuclei enough energy to overcome the repulsive force. The answer is not A because the product of the hydrogen fusion shown in the reaction is helium. Helium is an inert gas. The answer is not C because the hydrogen is a very abundant element. It is the most common element in the universe. The answer is not D because hydrogen fusion would produce a huge amount of energy. This literature which we use just to revise, that is written by Miss Leander. I have taken this literature from the website Save My Exam. So stars, the first thing which we are going to study is the Milky Way. Galaxies are made up of billions of stars. The universe is made up of many different galaxies. The sun is one of billions of stars in a galaxy called the Milky Way. Other stars in the Milky Way galaxy are much further away from Earth than the sun is. Some of these stars also have planets which orbit them. So our solar system is just one out of potentially billions in our galactic neighborhood, the Milky Way. There are estimated to be more than 100 billion galaxies in the entire universe. Astronomical distances, such as the distance between the stars and galaxies, are so large that physicists use a special unit to measure them called the light year. 1 light year is the distance traveled by light through the vacuum or of space in 1 year. The speed of light is the universal speed limit. Nothing can travel faster than the speed of light. But over astronomical distances, light actually travel pretty slow. The diameter of the Milky Way is approximately 100,000 light years. This means that light would take 100,000 years to travel across it. 1 light year is 9.5 expo 12 kilometer, or you can say 9.5 expo 15 meter. Life cycle of star. Life cycle of star nebula. All stars form from a giant interstellar cloud of hydrogen gas and dust called a nebula. Protostar. The force of gravity within a nebula pulls the particles closer together until it forms a hot ball of gas known as a protostar. As the particles are pulled closer together, the density of the protostar will increase. This will result in more frequent collisions between the particles, which causes the temperature to increase. Main sequence star. Once the protostar becomes hot enough, nuclear fusion reaction occurs within its core. The hydrogen nuclei will fuse to form helium nuclei. Every fusion reaction releases heat and light, energy which keeps the core hot. Once a protostar is formed, its life cycle will depend on its mass. The different life cycles are shown below. So here we have stellar nebula, then protostar is formed, then the main sequence star, and after this, the life cycle depends upon the size of the star. Star about the same size as the sun, they will convert into the red giant star, then they will form the planetary nebula, then a white dwarf, and then a black dwarf. The stars much bigger than the sun from the main sequence star, they convert into the red supergiant star, then a supernova, and then a neutron star or a black hole. The flow diagram shows the life cycle of a star which is the same size as the sun, solar mass, and the life cycle of a star which is much bigger than the sun. So we can reduce the size so you can see this whole. So this is the whole. So once a star is born, it is known as a main sequence star. During the main sequence, the star is in equilibrium and is said to be stable. The inward force due to gravity is equal to the outward pressure force from the fusion reaction. Red giant or red supergiant. After several billion years, the hydrogen causing the fusion reaction in the star will begin to run out. Once this happens, the fusion reactions in the core will start to die down. This causes the core to shrink and heat up. The core will shrink because the inward force due to gravity will become greater than the outward force due to the pressure of the expanding gases as the fusion dies down. A new series of reactions will then occur around the core. For example, helium nuclei will undergo fusion to form beryllium. These reactions will cause the outer part of the star to expand. A star the same size as the sun or smaller will become red giant. A star much larger than the sun will become a red supergiant. It is red because the outer surface starts to cool. For red giant stars, planetary nebula, once this second stage of fusion reactions have finished, the star will become unstable and eject the outer layer of dust and gas. The layer of dust and gas which is ejected is called a planetary nebula, white dwarf. The core which is left behind will collapse completely due to the pull of gravity, and the star will become a white dwarf. The white dwarf will be cooling down. As a result, the amount of energy it emits will decrease. Black dwarf, once the star has lost a significant amount of energy, it becomes a black dwarf. It will continue to cool until it eventually disappears from sight. So here we have the life cycle of a solar mass star and stellar nebula, then it converts to the protostar, then it converts to the main sequence star, then it forms red giant, and then planetary nebula, then white dwarf, and then black dwarf, and then it disappears. Okay, so for the red supergiant supernova, once the fusion reaction inside the red supergiant finally finishes, the core of the stars will collapse suddenly, causing a gigantic explosion. This is called supernova, At the center of this explosion, a dense body called a neutron star will form. The outer remnants of the star will be ejected into space during the supernova explosion, forming a planetary nebula. The nebula from a supernova may form new stars with orbiting planets. Neutron star or black hole. In the case of the biggest stars, the neutron star that forms at the center will continue to collapse under the force of gravity until it forms a black hole. A black hole is an extremely dense point in space that not even light can escape from. So here we have a diagram which shows the life cycle of a star much larger than our sun. So stellar nebula, it converts into protostar, that converts into the main sequence star. From there, it converts into the red supergiant star, then supernova, then neutron star, and the black hole. The literature which we are studying is written by Miss Leander. The expanding universe, galaxies, and the redshift. Usually, when an object emits, usually when an object emits waves, the wavefront spread out symmetrically. If the wave source moves, the waves can become squashed together or stretched out. So, for example, in this diagram, you can see this source which is producing the waves. It is stationary. So, in all directions, the wavelength remains same. But if the object is moving, for example, in this direction, and the waves which are reaching here, their wavelength will be smaller, but the waves which are reaching behind this moving object, here the wavelength will be larger. The diagram showing the wavefronts produced from a stationary object and a moving object. A moving object will cause the wavelength, lambda, and frequency of the waves to change. The wavelength of the waves in front of the source decreases and the frequency increases. The wavelength behind the source increases and the frequency decreases. This effect is known as Doppler. This effect is known as Doppler effect. The Doppler effect also affects the light. If an object moves away from an observer, the wavelength of the light increases. It is known as redshift as the light moves towards the red end of the spectrum. Redshift is an increase in the observed wavelength of electromagnetic radiation emitted from receding stars and galaxies. So here you can see a light from a star that is moving towards an observer will be blue shifted, and light from a star moving away from an observer will be red shifted. So this star is blue shifted because it is moving towards, and this is red shifted because it is moving away the observer. So objects not moving relative to the observer, the wavelengths, the frequency in all directions remains the same. Here we have if the source which is producing the waves, if it is moving towards the observer, this observer, for example, it will receive the waves with a smaller wavelength and higher frequency than the original one. This observer from the source is moving away from it, so the frequencies which the waves which it will receive, their wavelength will be larger and their frequency will be smaller. So it will be observing low frequency. This person will be observing higher frequency waves because the source of the waves is moving towards this observer. The observer behind observes a redshift. So this will observe a redshift. This person will observe a blue shift. The Milky Way is just one of billions of galaxies that make up the universe. Light emitted from distant galaxies appears redshifted when compared with the light emitted on Earth. The diagram below shows the light coming to us from a close object such as the sun, and the light coming to us from a distant galaxy. So you can see these bars. This is light spectrum from a close object such as the sun. So look at these bars, these lines. So the same lines have moved little towards this red color. This is light spectrum from a distant galaxy. So this line has moved to the red color, and this line also has moved to the red color. This line was here, it has moved to this direction. These two bold lines have moved towards the red. So this is showing a red shift. Comparing the light spectrum produced from the sun and a distant galaxy. The diagram also shows that the light coming to us from distant galaxies is redshifted. The lines on the spectrum are shifted towards the red end. This indicates that the galaxies are moving away from us. If the galaxies are moving away from us, it means that the universe is expanding. The observation of redshift from distant galaxies supports the Big Bang theory. Another observation from looking at the light spectrums produced from distant galaxies is that the greater the distance to the galaxy, the greater the redshift. This means the further away a galaxy, the faster it is moving away from us. So here we have a graph which shows the greater the distance to a galaxy, the greater the redshift. Here is the distance, here the redshift. As the distance from the observer increases, the greater is the redshift. The literature which we have just used is written by Miss Leander, and I have taken it from the website Save My Exam. The Big Bang theory, the Big Bang around 14 billion years ago. The universe began from a very small region that was extremely hot and dense. Then, then there was a giant explosion, which is known as the Big Bang. This caused the universe to expand from a single point, cooling as it does so to form a universe today. Each point expands away from the other. This means this is seen from galaxies moving away from each other, and the further away they are, the faster they move. Redshift is in the light from distant galaxies is evidence that the universe is expanding and supports the Big Bang theory. As a result of the initial explosion, the universe continues to expand. So here we have a diagram which shows all galaxies are moving away from each other, indicating that the universe is expanding. These are representing as galaxies, and they are moving away from each other. An analogy of this is points drawn on a balloon where the balloon, so here we have, you can try to understand. Here we have balloon, and a balloon inflating is similar to the stretching of the space between galaxies. So these red dots represent the galaxies. So as you will inflate, they will move away from each other. So he says that an analogy of this is points drawn on a balloon where the balloon represents space and the points on as galaxies. When the balloon is deflated, all the points are close together and an equal distance apart. As the balloons expand, all the points become further apart by the same amount. This is because the space itself has expanded between the galaxies. So I hope you understand this. So we have redshift and CMBR. Evidence for the Big Bang. The Big Bang theory is very well supported by evidence from a range of sources. The main pieces of the evidence are galactic redshift and the cosmic microwave background radiation. cosmic microwave background radiation, CMBR. Evidence for the galactic redshift. Galactic redshift provides evidence for the Big Bang theory and the expansion of the universe. The diagram below shows the light coming to us from a close object such as the sun and the light coming to the earth from a distant galaxy. So the light spectrum from a close object such as the sun and the light spectrum from a distant galaxy. Comparing the light spectrum produced from the sun and the distant galaxy, you can see these bands. They are here. They are going towards the red. So redshift provides evidence that the universe is expanding because redshift is observed when the spectral lines from the distant galaxy move closer to the red end of the spectrum. This is because light waves are stretched by the expansion of the universe, so the wavelength increases or frequency decreases. This indicates that the galaxies are moving away from us. Light spectrums produced from distant galaxies are redshifted more than nearby galaxies. This shows that the greater the distance to the galaxy, the greater the redshift. This means the further away a galaxy is, the faster it is moving away from the sun. These observations imply that the universe is expanding and therefore support the Big Bang theory. So here we have tracing the expansion of the universe back to the beginning of time leads to the idea the universe began with a Big Bang. Evidence from CMB radiation. The discovery of the CMB, cosmic microwave background radiation, led to the Big Bang theory becoming the currently accepted model. The CMB is a type of electromagnetic radiation which is a remnant from the early stages of the universe. It has a wavelength of around 1 millimeter, making it a microwave, hence the name cosmic microwave background radiation. In 1964, astronomers discovered radiation in the microwave region of the electromagnetic spectrum coming from all directions and at all generally uniform temperature of 2.73 Kelvin. They were unable to do this any earlier since microwaves are absorbed by the atmosphere. Around this time, space flight was developed, which enabled astronomers to send telescopes into orbit above the atmosphere. According to the Big Bang theory, the early universe was an extremely hot and dense environment. As a result of this, it must have emitted thermal radiation. The radiation is in the microwave region. This is because over the past 14 billion years or so, the radiation initially from the Big Bang has become redshifted as the universe has expanded. Initially, this would have been high energy radiation towards the gamma end of the spectrum. As the universe expanded, the wavelength of the radiation increased. Over time, it has increased so much that it is now in the microwave region of the spectrum. So here we have a diagram. So the CMB is a result of high energy radiation being redshifted over billions of years. So here when time 300,000 years after the Big Bang, temperature is 3000 Kelvin. And when it is redshifted 14 billion years after the Big Bang, which is the present, it represents 3 Kelvin. Okay, so the CMB radiation is very uniform and has the exact profile expected to be emitted from a hot body that has cooled down over a very long time. This phenomenon is something that other theories such as the steady state theory cannot explain. So here we have the CMB is represented by the following map. So let me reduce the size so you can see. So the CMB map with areas of higher and lower temperature, places with higher temperature have higher concentration of galaxies, suns, and planets. Cooler temperature, lower density of the galaxies, warmer temperature, higher density of the galaxies. This is the closest image to a map of the observable universe. The different colors represent different temperatures. The red, orange, brown regions represents warmer temperature, indicating a higher density of galaxies. A blue region represents cooler temperature, indicating a lower density of galaxies. The temperature of the CMB radiation is mostly uniform. However, there are minuscule temperature fluctuations on the order of 0.00001 Kelvin. This implies that all objects in the universe are more or less uniformly spread out. So measuring galactic speed and distances. Using redshift observations to measure the universe, the change in wavelength of galaxy is straight star light, due to redshift can be used to find the velocity v with which a galaxy or any distant object is moving away from Earth. Using an equation to compare the ratio of the expected wavelength with the observed wavelength, the velocity can be found. So the difference between the actual wavelength and expected wavelength divided by the actual wavelength is equal to the speed of the galaxy divided by the speed of the light. This equation will not be directly examined, but the idea that the velocity of distant objects can be found from the redshift seen is easily observed wavelengths is an important one. Measuring distance using supernova. Redshift and CMB radiation allows various measurements of the universe to be accurately made. Measuring distance is done using different methods. A key method is to use of the standard candles, including supernova. Supernova are exploding stars. Certain types have the same peak level of brightness, absolute magnitude, making them extremely useful in measuring the distance to remote stars and galaxies. Type 1a supernova are so bright that they can be seen clearly even though they may be deep inside their parent galaxy. This allows the distance to the galaxy to be calculated. This literature which we are studying was written by Miss Lindsay, and I have taken this literature from the website Save My Exam. Hubble and the age of the universe. Hubble constant calculations. In 1929, the astronomer Edwin Hubble showed that the universe was expanding. He did this by observing that the absorption line spectra produced from the light of distant galaxies was shifted towards the red end of the spectrum. This Doppler shift in the wavelength of the light is evidence that distant galaxies are moving away from the Earth. Hubble also observed that light from more distant galaxies was shifted further towards the red end of the spectrum compared to the closer galaxies. From this observation, he concluded that galaxies or stars which are further away from the Earth are moving faster than the galaxies which are closer. So, very distant galaxies, you can see these bands, they are more towards the red. Distant galaxy, this band is here, and nearby galaxy, the same band is here. For nearby star, same band is here. It's near the blue one. Laboratory reference is here. So the wavelength of the same lines when the galaxy is at a distance is very far away, then these patterns, they are more towards the red. So Hubble's law state that the recessional velocity v of a galaxy is proportional to its distance from the Earth. Hubble's law can be expressed as a H naught is equals to V by D, where H naught Hubble constant, this will be provided in your examination along with the correct units. And the accepted value for the H naught is 2.2 expo 8 minus 18 per second. And V is the recessional velocity of an object, the velocity of an object moving away from an observer. D is the distance between the object and the Earth in kilometers. As the equation shows, the Hubble constant H naught is defined as the ratio of the speed at which the galaxy is moving away from the Earth to its distance from the Earth. Age of the universe. Since Hubble's law states that H naught is equals to V by D, it can be rearranged to show that 1 by H naught is equals to D by V. Hubble's law shows that the further here from here you will get the time. Hubble's law shows that the further away a star is from the Earth, the faster it is moving away from us. So here we have recession velocity. Here is the distance. So as the distance from the Earth will increase, the recession velocity will increase. More distant galaxies are moving away at a faster velocity. And the gradient is equal to the Hubble's constant here. Galaxies closer to the Earth are moving away at a slower velocity. A key aspect of Hubble's law is that the furthest galaxies appear to move away the fastest. The gradient of the graph can be used to find the age of the universe. When the distance equals 0, this represents all the matter in the universe begins at a single point. This is the singularity that occurred at the moment of the Big Bang. The units of the gradient are per second, the same as the unit of the Hubble constant. By taking the reciprocal or 1 by h naught, the units will become seconds. Therefore, the reciprocal of the gradient represents the time and gives the amount of time which the universe has been expanding for. Astronomers have used this formula to estimate the age of the universe at about 13.7 billion years. So here we have a worked example. A distant galaxy is 20 light years away from Earth. Use the Hubble's law to determine the velocity of the galaxy as it moves away from Earth. And the Hubble's constant is currently agreed to 2.2 expo minus 18 per second. 1 light year is approximately 9.5 expo 15 meter. So the list, here we have the list of the known quantities. The D is 20 light years, and the Hubble constant is 2.2 expo minus 18 per second. So step number 2 is convert the 20 light years to meters. So 1 light year is 9.5 expo 15 meter. So you will have 20 light years equals to 20 multiply 9.5 expo 15. That will be 1.9 expo 17 meter. So just put the values there from the data booklet. You will have Hubble's law is V is equals to H naught multiplied D. So V will be equals to 2.2 expo minus 18 multiply 1.9 expo 17, and you will get 0.418 meter per second. Step 4, confirm your answer. The velocity of the galaxy as it moves away from the Earth is 0.42 meter per second. The literature which we are using we have used for this topic, that is written by Miss Lindsay, and I have taken this literature from the website saved my exam. So this is all about the space physics in the IGCSE physics, because this is the new topic which is added into the Cambridge O levels physics. So from everywhere, from wherever we get the material on the space physics, we are trying this. You see, whenever my students prepare the physics, they will be preparing the physics from not just one book. They will be studying two, three, four books, and the same topics they will study from different books. This is how you master a concept. So, my dear students, thank you very much for your patience. If you are watching this video and you think that this video has helped you to revise this topic, please share the link of this video onto your into your Twitter account, onto your Facebook, and onto your Instagram. This will help me to promote my channel. So thank you very much. Have a good day. God bless you all.